Hello guys, good evening everyone and welcome back to 360DigiTMG's domain analytics program. So it is the seventh day of transportation domain analytics. We've been discussing about machine learning usage when it comes to transportation analytics. How can we use machine learning and where exactly we need improvements when it comes to transportations? What are the things that we can do using the machine learning as well as the AI? So those applications we have discussed on the very first day, and then we have discussed what are the crisp ML methodologies. How can we process or to do the data science project? Whenever you are doing the data science project, you need to follow 6 phases. Those are called crisp ML. Crisp ML2, cross-industry standard process, machine learning quality assurance. So it could be any domain. Last time, the very first domain that we have discussed in this series was healthcare domain. In that also we have used the same crisp ML methodologies, and after that we have discussed web and mobile analytics. Same crisp ML methodology we are supposed to apply, and now we are discussing the transportation analytics. In this also we are applying the same crisp ML crisp ML methodologies. So we have discussed right very for second day actually what are the crisp ML methodologies we'll be having, what are the six phases, what we will be doing in each phase. So those things we have discussed. If you haven't watched healthcare analytics and mobile web and mobile analytics, in that case you can simply go to 360DigiTMG page, and there you will be getting all the domain analytics program playlist you will be getting. Simply you can watch those analytics from there. And after the second day, we have discussed different machine learning techniques we'll be having. Whatever the machine learning technique we'll be having, like supervised and unsupervised. So what is the difference between both, and how we can do the EDA, exploratory data analysis, and what are the pre-processing techniques we'll be having. Pre-processing techniques we'll be having, that we have discussed on the third day of this transportation analytics. And then we have taken on the fourth day one use case scenario in transportation analytics using what? Unsupervised learning. In that unsupervised, we have taken one specific algorithm called k-means. We have taken k-means algorithm, and we have tried applying in the real-time case scenario, and using that we have done segregations. And then we have taken one supervised, and fifth day we have taken one supervised algorithm. I hope you guys now know the difference between what is supervised, what is unsupervised. What are the pre-processing techniques we'll be having when it comes to structured data? What is structured data? What is unstructured data? In supervised, what we did, we have taken one algorithm called KNN, K nearest neighbor algorithm, and we have taken one use case scenario, and we have gone through that, and we try to apply that KNN machine learning algorithm. What is the working principle behind that we have seen, and then we have applied one use case scenario. And yesterday we have seen decision tree algorithm. It is one of the important algorithms when it comes to machine learning. In decision tree algorithm, how the decision tree works, what is the principle behind it, how it is forming the root nodes, and how it is selecting the root nodes, what is the greedy algorithm, So those are the things that we have seen yesterday, and we have taken one use case scenario, one use case, and we have applied the decision tree based model, that is random forest, and we have done predictions. That is on 6th day. So today is the 7th day of domain analytics program when it comes to transportation. And today we will be discussing about one of the, it is also supervised algorithm. Supervised algorithm means, I hope you have an idea about that. Anyway, simply I'll go through it, quick review. So whenever you have data set, in the data set, if you have an output column or label column or output column, in that case we'll be calling it as supervised model. So here we'll be having inputs x2, x3. So normally you will be having the features. I'm randomly taking x1, x2, and x3. These are the input features, and here we will be having output. When you have output or labeled column in your data set, in that case, you can simply go with supervised. When you don't have, in that case, we have to go with what? Unsupervised algorithm. Among that, among those supervised algorithm, we have classified into two classification, and we have regression. So what happens in classification? I hope you have an idea, since we have discussed on the last two sessions. We have taken the classification algorithm only, right? So here what we are taking, what is classification? Whenever you have a data frame, in that data frame, if you have an output, in that case, we'll be calling it as supervised. In that output, if you have categorical or discrete, if you have a data in the form of categorical or discrete, in that case, we will be going with what? Classification case. In your data frame, that is in labeled column. Labeled means output column. If the data is in the form of categorical or discrete, in that case, we will be calling it as classification case. If it is in the form of continuous form, decimal form, you can say, in that case, we'll be calling it as regression. The same output, if you have the decimal outputs, decimal data or continuous data, in that case, we'll be calling it as regression. So this is the difference between classification and the regression. So if you haven't watched the previous use cases that have discussed, that is Kane and in transportation analytics, in that case you can simply go to 360DigiTMG channel, and there you can find in transportation analysis, and you will be having different use case scenario. You can simply watch from there. Before getting into the today's the main topic, linear regression, we will go through what is the agenda for this today. So yeah, agenda for today's session is, first we will go through what is regression analysis, that we have I think I have covered that. Regression analysis, and then we will be having the linear models. What is linear model? And we will be going through the correlation analysis. So I hope you guys have an idea about correlation. When you want to find out the similarity or the relation between two variables, in that case, we'll be going with correlation. We'll be finding out the relation between two variables. In that case, we'll be calling it as correlation. Simply, we are to find out that we will be using the scatter plot. Scatter plot, it is bivariate analysis, but we will be doing x and y. So x is one variable and y is one variable. We are simply plotting the x and variables on the plot, 2D plot. That is what we'll be doing when it comes to correlation analysis. And equation of the straight line. So when it comes to linear model, what will be the equation of the straight line that we will discuss, and then we will be discussing about simple linear regression. What happens in the simple linear regression? So when we'll be calling it as a simple linear regression, we'll discuss. And then we have a transformation. So when exactly we will be using the transformation, that we will see. What is the need when it comes to transformation? That is also we will discuss. And then we will discuss bias and variance. What is the bias and what is the variance? Normally, when you have high training accuracy and less testing accuracy, in that case, we'll be calling it as variance, or also called as overfitting. And when it comes to bias, when you have a training accuracy itself less and testing accuracy, in that case, anyway, it is less. In that case, we'll be calling it as bias, or you can also call it as underfitting. And then we'll be taking one use case scenario, business use case scenario, use case we have. That use case we will be discussing, and we'll try to apply the linear regression model using the one use case scenario, and we'll try to do the prediction. So this is the agenda for the today's session, and yeah, without wasting any time, let's get into the session. Yeah. Regression analysis. Regression is used to study the relation between two. So it is a kind of correlation. So we will be using the regression to study the relation between two variables. We can use simple regression if both dependent variable and independent variables are numerical. So normally when you have just one input and of course one output you'll be having. When you have just one input, in that case, we'll be calling it as simple linear regression. Simple linear regression. When you have more than one input, in that case, we'll be calling it as multiple linear regression. The dependent variable is numerical, but the independent variable is categorical. It is best use case of ANOVA. So when the independent variable, that is X input, is categorical, and when you have dependent variable is the numerical. Of course, then only we'll be going with a regression case, right? Output is numerical, that is continuous, and independent variable is categorical. It is the best use of ANOVA. In that case, what we'll be doing, we'll simply converting whatever the categorical values will be having into discrete, and then we will be applying the simple linear regression. So when you have independent variables as a continuous value, in that are numerical values, simply we'll go with the linear regression, simple linear regression. But it is not the case. In that case, we will be converting into discrete values. So these are the situations where exactly we will be using the regression. Testing of IQ affects income. So normally what we will be doing, see, IQ. A person's income will be depending on IQ, right? If IQ is increasing, in that case, you can say, right, income is also increasing. Here we'll be having just one input. In that case, we can simply use simple linear regression. Testing if IQ affects income. IQ is an independent variable and the income is a dependent variable. Testing of hours of work affect the hours of sleep. Definitely, right? Dependent variable here is hours of sleep, and the hours of work is an independent variable. So using just one input, we will be predicting the other output. Testing if the number of cigarettes smoked affect the blood pressure. The number of cigarettes smoked here will be using as an independent variable, and the blood pressure will be using as a dependent variable. Since we have just one input, based on that, we'll be finding out the output. That is the case, we will be using the simple linear regression. So these are the small examples where exactly we can use the simple linear regression. So before getting into the regression, you have to know what is the correlation. You have to plot. Do you have any correlation between the input variable and output variable? When you have correlation in between input variables and output variables, in that case only we can go with the regression. Why? Because if you don't have any correlation between X, that is input, and output, in that case, if both are independent each other, in that case, we don't need to go for regression at all. It should be what is regression, whatever the input changes that you are doing, it should reflect on the output. That is the reason we'll be using it. There is the correlation. That is the correlation. Let's say here it is IQ and income. IQ is increasing. In that case, income is also increasing. Here we can say it is a positive correlation. And you can say actually strong positive correlation. Since it is strongly, the correlation is very strong. It is important to perform scatter plot because it helps us to see the relationship is linear or not. First, we have to find out whether you have a correlation or not. What kind of correlation will we have? If you have linear correlation, in that case, you can simply go with the linear model. If it is not having the linear correlation, if you apply the linear model, in that case, you will be getting so much error. So because of that, you have to know which kind of correlation you will be having. So this is linear correlation, but it is not a linear correlation. If you don't know what kind of correlation it will be having, and if you randomly or blindly apply the linear model. So here, if you apply a linear model, in that case, we'll be getting good, great accuracy actually. Not just good, we'll be getting good accuracy since are highly correlated. But here, without looking into the correlation, if you apply some random regression line, in that case, you will be getting so much error. Let's say like that you have applied the regression line. There is a prediction line, or we can say regression line. In that case, you will be getting so much error. So it is very important to know what kind of correlation you will be having among the variables. So here it is an example for what? Body fat and chance of heart failure. So it is if your body fat is keep decreasing, at one point it will reach minimum, and the heart failure chances. So when you increase the body fat, in that case it will again start increasing. So at one point when you have less body fat, that is also increases your heart failure. So you need to have minimum body fat, this much of body fat, so that you can maintain a healthy life. Even though if you have less body fat, that is also increase the chance of heart failure. If you have body fat more than limit, in that case also it will increase the chances of heart failure. So you should maintain some. Yeah, you should maintain some body fat in order to avoid those heart failure, chance of heart failure. So this is the correlation you have to find out very first. First, you have to find out the correlation, then only you can get into the regression. So here you can see these are the different scatter plots. They are the different scatter plots, and how these are correlated, that we will find out. Scatter diagram provides the plots. It is a bivariate since we will be having something on X and something on Y. So this is the data frame and it is the correlation. So one thing you have to remember, correlation doesn't guarantee the causation. Causation means you might have an idea like cause and effect. You will be having relation, right? Cause and effect. Correlation doesn't guarantee the cause and effect relation. Like what? You smoking makes, because of smoking, you might be getting the cancer. It is a cause of smoking, and you will be having the, because of smoking, you might have the cancer. It is a causation relationship. But Here, whatever the correlation will be having, it doesn't guarantee the causation. You should keep this in mind before you are working on the correlation. Correlation doesn't guarantee the causation. It doesn't guarantee the causation. So here you can see, as X is increasing, Y is also increasing. In that case, you can say you have a positive correlations. And if you draw one regression line along the point, I mean, you will be doing the multiple iteration, then you will be coming up with one regression line. If all those points are on that particular regression line, in that case, you can say it is the strong correlation. You can say it is a strong correlation. But if you see the most of the data points are near around it, in that case, what you can say? It is a moderate positive correlation, but it is increasing, right? As X is increasing, Y is also increasing. It is also positive correlation, and it doesn't matter if it is positive, X is increasing or not. In this case, we'll be having no correlation. We can say no correlation. And if X is increasing, Y is decreasing. In that case, we'll be having the negative correlation. And also if that is on the most of the data points are present on the line, in that case we can say it is a strong negative correlation. Here we have moderate negative correlation. Here it is not a linear, it is a curvilinear relationship. These are the different relationships that you have to correlation, you can simply say, you have to be aware of before getting into the regression. So these are the relationships we have. See, we are just qualitative. It is you can say whatever the terms that we are using: strong, moderate, no correlation. These are all what? Qualitative. So in order to quantify, we will be using what? Correlation coefficient. To quantify correlation coefficient. To quantify this correlation relationship, we will be using the correlation coefficient. Instead of quality, it will show you how much correlation will be having. If it is having the 80% correlation, 50%, 60%, we'll be knowing using the correlation coefficient. If you have correlation more than 85, in that case, we will be calling it as strong correlation. If it is less than that, in that case, we will be calling it about moderate to correlation. If you have less than 45, in that case, we will be calling it as poor correlations also, you can say. So when it comes to linear regression line equation, linear model, what is linear model? Linear model is just line equation. So here you can see y is equal to, so what is the linear equation line? Y is equal to mx plus c, right? That is the line equation. Similar to that, we will be having bx plus e. Bx plus e. Here we will be having y is a dependent variable. Using this, we will be calculating the y value, and here we will be having x independent variable. Here in the case of whatever the example that we have discussed here, we will be having the income as a y, and input, that is independent variable, we are taking it as q, and a is an intercept, y-intercept you can call it, or you can say it is a constant. And here b is a coefficient of this feature x, that is feature of q. And e is the error term we will be having, additional variant not explained by the income. It is an error term. The error is, it should be, when it comes to error properties, we'll be having error should be normally distributed. What is the normal distribution? We'll be having, so bell-shaped curve. It should be in the form of bell-shaped curve. This can be, you can simply do the histogram. In that case, you can simply easily figure out whether it is normal or not. So this is a linear model. In this only we'll be applying the linear regression. So I've told you, right, how can we quantify whatever the correlation will be having? For that, we will be using the correlation coefficient. So we will be having the positive correlation and we will be having negative correlation. It doesn't matter whether it is positive correlation or the negative correlation. We'll be taking both. It doesn't matter. Anyway, we'll be taking R in mod. So whatever the correlation will be having, you'll simply converting into positive one. So it doesn't matter whether it is positive or negative. We'll be considering that correlation. So this correlation ranges from -2 to +1. The correlation will ranges from -1 to +1. When you have perfect correlation, perfect positive correlation, in that case will be taken as +1. If it is perfect negative correlation, in that case will be taking it as -1, and if it has no correlation, in that case will be considered as 0. Here you can see these are the data points are actual, and this is the predicted line. You can say in that case we have correlation is about 0.4. Here we don't have any correlation. No data point is present on the regression line. In that case will be considered as 0. That is no correlation. Here you can say negative correlation. As X is increasing, the Y is decreasing. In that case, we'll be taking it as negative correlation. If you want to find out that correlation, you can simply use that X and Y values into this formula. You can simply get the what is the correlation value, correlation coefficient of that particular feature, those two variables. So this is quantifying the correlations. Whatever the quality, you are talking about, right? Qualitative, strong, medium, high, low, something like that. That we will be quantifying it. Based on that, we can simply say that this is a strong correlation and this is medium, average, or you can say low correlation. Ordinary least square error. Let's say these are the two variables we'll be having. This is X and it is Y. Let's say it's input. It is output and it is input. So these are the real data points. These are real data points. These are all real data points. It is the output, Y you can say, and it is X. So when you represent all the X and Y values, you will be getting this. And using these data points, I will be using what? One regression line. One regression line. I'm drawing one regression line here. I'm not directly drawing the regression line, right? It's here only. I'll be doing multiple iterations. So algorithm, the decision tree algorithm will do multiple iterations and it will calculate the error term. So here what is regression line? It is a predicted line, you can say. Equation of the predicted line is what? Beta naught plus beta 1 into X. What are the beta 1, beta 2, beta naught and beta 1 here? Coefficients. What are those coefficients? It is a constant value beta naught and it is coefficient value for that particular feature. So I will be getting, when you are building a model, it will automatically assign the coefficient value. So what we are doing here, we will be doing multiple iteration. Let's say here, first we will be drawing one regression line or the prediction line, you can say. Here you can draw something like that. Maybe you are drawing something like that. And then what you are doing, we are checking the error. So this is the predicted line and it is the actual value. Whatever the distance will be having, that only will be calling it as error, right? You can simply represent that error is equal to Y minus Y predicted. So it is the actual value and it is a predicted value. Whatever the difference will be getting, that is only will be calling it as error. So let's say first we have done this. In that case, what is the error? So this is all error only, difference only, right? It is a predicted line and this is error. Again, I'll see how much error I'm getting. I'm simply calculating the error, which is what? RMSE. Root mean square error. We are simply squaring that particular difference and then we are root squaring. So in that case, we will be getting the exact value. When you use mean square error, mean of all, you will be getting 0. As always, you will be getting 0. When you calculate the difference or errors mean, in that case, we will be getting 0. In that case, to avoid that, we will be going with root mean square error. We'll be finding the root means first we'll be drawing one and then we'll be finding the root mean square error. Again, it will be drawing one more and it is finding the root mean square error. Again, it will find something like that. It will do multiple iterations. Finally, wherever you are getting the least square error, mean square error, right? Root mean square error. Wherever it is the least, that regression line will be considering as the best fit. Wherever it is less, error, that is only we will be considering as the best fit. So here we will be taking it as best fit. So like that, we will be selecting the regression line or the best prediction line. That is only we'll be calling it as what? Ordinary least square. That is only we'll be calling it as what? Ordinary least square. Ordinary least square, what it will do? Is a common technique for estimating the coefficients of the linear regression equation, which describe the relation between one or more independent quantitative variables. We are not talking about the the qualitative. It is quantity at a dependent variables, simple or multiple linear regression. Here we are using. We can use both simple linear regression. You can use multiple linear regression. Use simply based on the error term. It will simply figure out which is the having the least RMS square value, and that only will be considered. So this is ordinary least square error, just to find out the best prediction line, or you can say regression line. Okay. So whatever the regression line that you are building or the model that you are building, how do I know that whatever the model that you are building is a good fit? How do I know? In that case, we'll be using the R square value, or you can simply say R2. In that, this is the coefficient of determination. What exactly the R square do? How we'll be finding the R square value? That it represents percentage of variation in output. Whatever the variation that we are getting in our output, not in our label column. So percentage of variation in output, that is in dependent variable, is explained by the independent variables, or that are also called as a input variables, or percentage of response variable variation, that is explained by its relation with one or more predictor variables. When you have just one input, in that case, what it is? Percentage variation, that is the change it is happening in the dependent variable, that is explained by the independent variable. That variation only it will be captured by the R. How much variation it is captured by that particular output or the input, in that case it will be using R. We will be deciding how much variation it is capturing. So higher the R square value, you will be getting the best. Whatever the model that you are using, it is the best fit model. R square values always it is in between 0 and 1. 0 and 1, or you can simply say 0 to 100. So whatever the R square value will be having, it is always in between 0 to 100. If R square value is in between 0.6 and 0.8, in that case we will be calling it as moderate. Whatever the model that you are building is moderate, and the correlation will be having moderate. If R square value is greater than 0.8, in that case we'll be calling it as, whatever the model that you are building, it is a good model. Whatever the model that you are building, we can say that model is a good model. And to find out the R square, will be using the actual value minus residual, that is actual value minus predicted one, and this is a predicted one minus residual. If you divide those, in that case we will be getting the R square value, and R square value it's always should be in between 0 and 1. So here we'll be having the confidence interval, prediction and confidence interval. What is the prediction interval? It simply represents whatever the values that are taken, that should be in that particular range. And the confidence interval, it represents the range that the mean response is likely to be found. Whatever the output that we are predicting, it should be present in that particular interval only. That is what it simply represents. You can always say the prediction interval is always wider than the corresponding confidence interval. So when it comes to simple linear regression, what we'll be having? So y should be whatever the output that we are having, it should be continuous. And whatever the input that you are reading, it should be also continuous. Then only you can simply go with simple linear regression. And if y is continuous and the input variable that we are using, it is not not a continuous value, in that case, what you have to do? If it is in the form of single and discrete, it should be single when it comes to simple linear regression, and it is a continuous. If it is single and it is not a continuous, in that case, we have to convert the discrete into dummy variable creation. You might have an idea about dummy variable. Simply, whatever the categorical or discrete value will be having, we are converting into dummy variable. And then we'll be doing the simple linear regression. So this is when you have a simple linear regression. What happens when multiple linear regression, MLP? Similar to that, same output will be the continuous, and whatever the input you will be having, multiple, those inputs should be multiple and it should be continuous. If inputs are multiple and they are not, some are not continuous, in that case, what you have to do? The same, you have to convert into dummy variable creation, and then you will be using that data for the regression. So I hope you guys have an idea about this. And when it comes to error variable, the error term is critical part of the regression model, since we'll be dealing with we have one property, right, for error term. It should be normal. 4 requirements involved in the distribution of error must be satisfied. The probability distribution of E should be normal. In that case, what? A distribution should be normal. The mean of the error, it should be 0. Yeah, it will be 0. The standard deviation of E of error is, let's see, for all the values of X. The set of errors associated with the different values Y are all independent. So whatever the values that you are getting right after the error, it should be independent. All are independent. Shouldn't be having any correlation right after the errors. So these are the requirements or condition when it comes to error will be having. So based on this, whatever the regression will be having, we'll simply see one use case scenario. What is the use case scenario? I'll give you one. What exactly the objective is. Based on that, we will get into it and we'll see what exactly we are doing when it comes to that use case scenario. In this use case scenario, I will be having different cars, different cars and their different features. So since it is simple linear regression, I'm using the multiple linear inputs. So same, the process will be the same, but instead of y is equal to beta naught plus beta 1 x, you will be having y is equal to beta naught plus beta 1 x1, beta 2 x2, beta 2 x3. So these are all what? These are the coefficient. Beta naught, beta 1, beta 2, beta 3. All are the coefficient. But one thing you have to keep in mind when you are working on the multiple linear regression, you have to look into those inputs as well. Make sure whatever the input that we are using doesn't have any correlation in between them. It shouldn't be having any correlation in between them. Why? Because if you have a correlation in between those input variables only, in that case, it will definitely affect the whatever the prediction that you are doing. So to avoid that, we have to make sure whatever the input features you are taking, it shouldn't be having correlation among them. It should be having correlation in between the inputs and the output variable, but not among them. In that case, if you have, in that case, we might be getting into the collinearity issue. In that case, you have to deal with that that collinearity issue, but make sure it is not having that correlation among the input features. The similar to say, we'll be using the multiple features, and we'll be doing it. So here what I'm doing, the objective of this use case is I have to predict the price of that particular vehicle, whatever the vehicle that I'm having. Based on those features, the brand, is also very important, right? Now, just to find out the features, price of that particular product, you have to look at the brand. Brand makes a lot of, it is important factor to predict the price of that particular feature, and whether what kind of engine it will be having, and drive, whether it is 4-wheel drive or 2-wheel drive or something like that, will be having full wheel drive. So these are the different features we'll be having. Using those features, we'll try to predict the price of that particular product. What are those features? All those things we will see in this Python file. Let me open that. Yeah, here it is one of the use case scenario that I'm talking about. Here I'm importing the NumPy as NP since we need to do the lot of mathematical calculations. So I'm using that, and again I'm using the matplotlib. Also I'm importing since I need to do the visualization and to do the modification in the data set, or to do the manipulation in our data set. The data frame I'm using pandas, and importing the data set using what? Pandas. Df is equal to, in df I'm storing all those information. When I use df.head, in that case we'll be getting, these are the features. Car ID will be having symboling, car name, what kind of car will be having, fuel type, which kind of car it is, fuel it is containing, aspiration, and door number, how many number of doors will be having, car body, convertible, hatchback. This also plays very important role to do the price prediction, right? So whether it is convertible or not, hatchback, sedan, driving, 4-wheel drive, full-wheel drive, road-wheel drive, something like that will be having, engine location, front or rear, and wheelbase clearance, how much we will be having, engine size is how much, fuel system, and bore ratio, stroke, under compression. These are the different features we'll be having. Based on that, this is the label column. Price, how much is that particular call price? It is in the form of dollars. So it is in the dollar form. So you can simply take this as an output variable, and you can simply build the model. So I'm checking the shape of that particular model. That is the 205. We have entries of 205 and 26 features we'll be having. I'm checking whether you have any null values or not. Let's see, there is no null values. And then I'll be having the car unique. How many unique cars will be having? These are different unique. In car name, how many unique will be having? So Alfa Romeo, these are the different cars name. Honda Accord, CVC, these are the different car names. For this, so these car names doesn't mean it is not useless feature. Whatever the car names it will be having, it is definitely plays very important role to find out the price of that particular car. So I am using one-hot encoding, or you can simply go with one-hot encoding. Doesn't give the order preference, so I'm simply going with the ordinal, and you can simply go with the label encoding as well. I'm simply doing the ordinal encoding. So I've converted whole car names into the ordinal encoding. Here you can see those ordinal encoding. Car name and the rest, whatever the car name will be having, I'm simply dropping that. Since that doesn't require, I just need brand name. And then, yeah, car ID. What are the features that are required for us and which are not required for all these features that are not required? I'm simply dropping those. Here, car ID is not required. So why it is not required? It is simple nominal data. It is not giving any information to find out the price of that particular model. So it is not necessary for us. So I'm simply dropping that one. And whatever the categorical values I'll be having. What else we have? So these are all categorical feature only, right? Field type we have just 1 or 2. So I'll be doing one manual encoding test. We have gas as well as diesel. So I'll be doing giving gas as 0 and diesel as a. You can simply map. You can map those since we have just 2. Like that, I will be doing encoding for the turbo. What kind of aspiration will be having, whether it is 100 or a turbo. For that also, I am giving 0 as 1. That is a mapping I will be doing. And like that, I will be doing pre-processing for each and every data. Here I am using door number. So it is also very important feature to determine the predict the price of that particular car. So here, whatever the door, we have just 2 doors in that case, I'm giving the 0. If we have 4 doors in that case, I'm giving as 1. I'm simply doing the mapping. Manual coding also you can say. Convertible, hatchback, sedan, wagon, hot dog. These are the different features. I mean, different cars. When it is a convertible, in that case, it will be pricey compared to the other, right? So it is following some order. In that case, I'm simply giving the ordinal encoding. I'm simply applying the ordinal encoding. So in that case, you can see these are all the ordinal encoding after doing the ordinal encoding outputs. And the rest core body I'm simply dropping, and then instead of that, whatever the encoded form will be having, I'm simply appending into the data frame. And then I have 4-wheel drive, road wheel drive, and full wheel drive. These are the. It is also having the some order. In that case, I'll be using here label encoding, and I've converted into the data, and whatever the data set it is having, I'm simply replacing with the encoded value, encoded data. Drive in, these are the label encoded form. Like that, and we'll be having front and rear in that case also. You can directly manual encoding you can give, that is 0 and 1, front for 0, and real we can simply give as 1. And then we have engine type. So these are the different engine type. It will be having some importance. So based on the engine also, based on engine, we can increase or decrease the price. So it will be very important feature. So what I'm doing, I'm simply applying the ordinal encoding for the engine type as well. And I'm simply replacing with feature that is will be having the category. And then I'm appending all those features into the data frame. Now you can see it is the data frame that we have to work on it. Here cylinder, it is one of the features will be having cylinder as well. That is also plays very important role since it is 4. It will be having order. So I'm doing the ordinal encoding for that, and I'm simply appending that into our data main data frame. And then we have fuel system. That kind of system will be whatever the category will be having, categorical values will be having. If it is following some particular order, in that case, what I have to do? I have to do label encoding or ordinal encoding based on the requirement. I'm simply doing here I'm doing the ordinal encoding, and then we have, so it is already appended, so we don't need that feature again. So I'm simply dropping it. So here I'm separating the X variable and Y variable. Here, other than the price, you can see, other than the price, since it is a price is a target, other than the price, everything I'm simply appending into the X variable. So it is the independent, all are what? Independent variables. And then we'll be having dependent variables is what? Price, that I'm putting in Y. I'm simply moving into the Y variable. And now I'm splitting the data into train, test, and split. Here I'm giving stress charge is equal to 0.3. That is 30% I'm giving for the test, and 70% I'm giving for train. So I'm simply here importing the linear regression. That is, since we are working on that particular feature only. And I'm simply initializing that, and I'm simply fitting into that regression with train data, X train and Y train. And here the test, I'm using test, I'm applying. These are the prediction that I have got. So for that particular feature, whatever the features will be having, these are the predictions I will be getting. To find out whatever the prediction that we are getting are exactly true or not, I'm simply importing the, I'm simply applying the regression score. How much we got? 85% we got So it is not bad value. And if I go with R square value, for that I have to import what? From SQL matrix, I'm importing the R2 square value, and I'm simply checking R2 square value. How much we got? 85%. So if it is more than 85. So you can say whatever the model that I'm building, it is a good fit. So I can simply go with. And if you want to do some improvements, in that case, you can check what kind of distribution it will be having each and every feature. Whatever the features will be having, whether we have any non-normal distribution or not. What is non-normal? If it is not present, whatever the features will be having, that is numerical feature I'm talking about. Whatever the numerical features will be having are not in the form of normal, that is bell-shaped curve, or you can say Bayesian, Gaussian form. In that case, what you can do? You can simply convert those non-normal data into normal data. That is, we'll be calling it as transformation that we have talked about, right? To convert non-normal distribution to normal distribution, we'll be using transformation. If you do the transformation, if any one of the features are not normal, in that case, you can simply do the transformation and you can again apply the model, linear regression model, and you can simply check this R value. In that case, you will definitely finding the improvement when it comes to R square value, since whatever the non-normal data will be having, that data we are converted into normal. So these are the modifications that you can do, and you can simply improve the this particular model. Since it is just presentation, so I have come up with only base model. There are so many improvements that you can do on this particular data. If you want, you can simply go to Kaggle, or you can import this data, download the data, and you can open it. So this is all about the linear regression. This is about the linear regression and how can we apply the linear regression using the one use case scenario. Here what we are doing, using the different feature, we are simply checking, simply predicting the price of that particular car. So yeah, that is it for today, guys. I hope you guys learned something from this class, and if you like this content, and if you want to see more of transportation analytics, in that case, today we'll be having one more class regarding that MLP, multi-layer perceptron. Using multi-layer, we'll be seeing what exactly MLP, and we'll be using one use case scenario, and we'll try to apply the multi-layer perceptron, and we'll do the prediction. And if you want to kickstart your data science career, in that case, you can simply go to Tame Python Sessions. Tame Python Session by Bharani. There you will be getting a playlist of Python videos that is very crucial for data science. You can simply go through it, and if you want, if you want to go through the contents like that, in that case, you can simply subscribe to 360DigiTMG channel, and you can go through all the analytics, different analytics we'll be having. You can simply go through it. And that is it for today, guys. I hope you guys learned something, and yeah, thank you for joining, and we'll see you in the next class with one more model and one more use case. Until then, and bye, and have a nice day.